Think about this right now. As you breathe, the entire solar system is gliding through the Milky Way at nearly 500,000 miles per hour. Every atom, every planet, every galaxy is spinning in a cosmic dance. Yet none of this motion reaches us. Why is everything in the universe spinning? And why can't we feel it? In this stillness lies the hidden rhythm of the cosmos, waiting to be discovered. Have you ever paused to wonder why everything in the universe is in constant motion, yet we ourselves feel perfectly still? The Earth spins at more than 1,000 miles per hour, circling the Sun from a distance of 93 million miles, while the entire solar system hurtles through the galaxy at nearly 500,000 miles per hour. And yet, we sense none of it. Our heartbeat stays calm. Our breathing doesn't sway as if we were locked inside a racing machine. It feels as though we are motionless, suspended in quiet. But what if that stillness is the greatest illusion of all? What if time itself is nothing more than the whisper of a deeper rotation, one that began before atoms, before light, before memory itself existed? Tonight, we drift into that mystery, not only to ask why things move, but why nothing can ever truly stop moving. So close your eyes, let the low hum of the cosmos settle beneath your skin, and follow me into the spinning core of everything. And before we begin, if you feel inclined, a gentle like or a quiet tap on subscribe would truly mean the world to me. It's a small gesture, but I hold it with sincere gratitude, because every bit of your support keeps this small universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let's begin with our first question. Part 1. If everything in the universe is spinning, why do we feel frozen in time? The Earth is rotating at over 1,000 miles per hour, turning steadily beneath your feet. At the same time, it races around the Sun at nearly 67,000 miles per hour. And as you breathe right now, the entire solar system glides around the Milky Way at almost 490,000 miles per hour. Yet somehow, none of this movement reaches us. The coffee in your cup remains smooth. The air doesn't tug at your skin. The stars appear fixed and unmoving. This is one of the deepest illusions of existence, a strange balance between motion and calm. From the tiniest electron to the largest clusters of galaxies, everything spins. Atoms rotate, planets revolve, galaxies twist into vast spirals of light and dust. Some cosmological models even suggest that the universe itself may carry a faint global rotation woven into its structure. But if everything is moving, why does it all feel so still? The answer begins with inertia, one of the quietest yet most powerful principles in physics. Isaac Newton described it in the 17th century. An object in motion remains in motion unless acted upon by an external force. This simple law explains why we don't feel the Earth's endless spin. We are moving with the planet, not against it. Your body, the air around you, the oceans, the mountains, all of it moves together, bound in a single, silent rhythm. To feel motion, there must be change, a push, a pull, a difference. But here, there is none. The Earth's rotation is smooth, constant, and ancient. It is the same today as it was when early humans first stared up at the night sky. Astronauts experience this illusion even more clearly. In orbit, they travel at around 17,500 miles per hour, circling the Earth every 90 minutes. Yet inside the spacecraft, everything feels peaceful, free of resistance, untouched by friction. Motion becomes indistinguishable from stillness. This effect is known as uniform motion. It's the same reason you can calmly sip tea on an airplane cruising at 500 miles per hour. You and the plane move together. Only when turbulence breaks that uniformity do you feel motion. The Earth's movement is just as seamless. No vibration, no drag, no sudden shifts. And because space is nearly a perfect vacuum, there is nothing to remind us that we are spinning at cosmic speeds. Neil deGrasse Tyson once said, "We are on a space rock orbiting a star, which itself orbits a galaxy, and we call it home." It's easy to forget because our senses were never designed for such scales. The inner ear, which governs balance and motion, evolved to manage walking, running, and climbing, not the rotation of a planet thousands of miles wide. It detects acceleration, not steady speed. That's why you feel a car start moving, but not its constant cruise. On Earth, everything moves with you. There is no beginning or end, only an endless glide. Still, scientists can measure this hidden motion with remarkable accuracy. The Foucault pendulum, first demonstrated in 1851 by Léon Foucault, swings freely while the ground beneath it slowly turns. It doesn't rely on the stars to prove Earth's rotation. Its gradual shift over hours quietly reveals the planet's spin. If you've ever stood near one in a museum, you've watched time and motion blend together, one gentle swing at a time. On a planetary scale, this rotation is anything but trivial. The Earth's spin creates day and night, helps sustain the magnetic field, and shields us from harmful solar radiation. Without it, one side of the planet would burn, while the other would freeze. Scientists at NASA's Goddard Space Flight Center have shown that Earth's rotation is slowly slowing down, largely due to the Moon's tidal pull, adding about 1.7 milliseconds to the length of a day every century. Even in stillness, change is happening, slow and nearly invisible, but real. When we look beyond Earth, rotation appears everywhere. Stars are born from collapsing clouds of gas and dust. As they contract, they spin faster, conserving angular momentum, the same principle that makes a figure skater spin more rapidly when pulling in her arms. Planets inherit this motion. The Earth's 24-hour day is a fossil record of that ancient cosmic whirlpool. The Sun itself rotates once every 27 days, stretching its magnetic field through space like glowing threads. And the Milky Way turns once every 230 million years, carrying hundreds of billions of stars in a spiral dance that began long before Earth existed. The James Webb Space Telescope has observed galaxies so distant that their light has traveled for more than 13 billion years to reach us. Even these early galaxies show evidence of rotation. Scientists detected subtle shifts in their light. One side slightly red-shifted, the other blue-shifted, a quiet signature of spin. It seems rotation is written into the universe at its deepest level. So how can everything be spinning, yet feel so calm? Part of the answer lies in relativity. Einstein showed us that there is no absolute motion, only motion relative to something else. From our position on Earth, we are at rest, and the universe moves around us. From another viewpoint, the opposite is true. This balance keeps the laws of physics consistent and turns stillness into a matter of perspective. Astronauts aboard the International Space Station orbit Earth at nearly 5 miles per second, yet they feel weightless, not fast. Their sense of direction shifts every 90 minutes, and still the mind adapts. We, too, are travelers in motion, adapted to calm. Our stillness is a kind of survival, a harmony between what our senses can handle and what the universe requires. If we truly felt the Earth's spin, the sun's pull, the galaxy's drift, our sense of time itself might collapse, because motion and time are inseparable. Rotation defines days and years, but it also sets the rhythm of the cosmos. Time, as Carl Sagan once said, is woven into the fabric of the universe, and we are part of that weave. The quiet you feel now is not the absence of movement. It is the harmony of everything moving together. So when you lie down tonight beneath the unseen turning of the stars, remember this. You are not standing still. You are drifting through a vast cosmic river, gently, endlessly. Every moment of calm is simply motion made too smooth to notice. And within that perfect balance of movement and peace, life finds its quiet rhythm. Take a slow breath. You are spinning. You always have been. And the silence you hear is the sound of everything moving together. Now, as we drift deeper into this story, let's look back to the moment before motion itself began, to the instant when the universe took its very first turn. That is where our next chapter begins. Part 2. Who set the universe spinning? If you could go back in time, not hundreds of years, not even thousands, but all the way to the very first second after the Big Bang, what would actually be there? Would there be light at all? Would there be sound? Or would there only be motion itself? A sudden stirring, a subtle twist, the first hint of rotation that everything in the universe would later inherit. The idea of what gave the universe its first spin isn't really a philosophical question. It's a physical one, hidden deep inside the math of cosmology, buried in the earliest instance of time, when matter, energy, and even space were only just beginning to exist. Scientists refer to this moment as the Planck era, an unimaginably brief slice of time, about 10 to the power of minus 43 seconds after the Big Bang, so early that our current understanding of physics simply breaks down. And yet, what little we can piece together suggests something surprising. The universe may not have begun in perfect stillness, but with a faint, primordial rotation. When scientists study the cosmic microwave background, the faint afterglow left behind by the Big Bang and measured by missions like NASA's WMAP and the European Space Agency's Planck satellite, they see tiny variations in temperature, differences so small they're measured in millionths of a degree. These irregularities show that the early universe wasn't perfectly smooth. Small differences existed, and over time, those differences grew into galaxies, stars, planets, and eventually life. But hidden within that background, some researchers noticed something even more unusual. A subtle alignment, a large-scale pattern, almost like the universe itself had a preferred direction. This strange feature became known as the axis of evil, a controversial signal that hints the universe, on its largest scales, might not be completely random. Data from WMAP and later from Planck suggest two possibilities. Either this alignment is a quirk of our measurements, or it's a real physical feature, evidence that the universe once carried an overall spin. If that spin is real, it may have shaped everything that followed, from the spiral structure of galaxies to the direction time itself seems to flow. So where could such a rotation come from? One possible answer lies in quantum fluctuations, tiny, unavoidable variations in energy that occur even in empty space. According to physicists at NASA's Goddard Space Flight Center, quantum fields are never truly still. They constantly jitter, even in a vacuum. When the Big Bang occurred, those tiny jitters were stretched dramatically during cosmic inflation, a brief period when the universe expanded at an extraordinary rate. That rapid expansion could have transformed small, random fluctuations into large-scale motion, including rotation. Inflation theory, first introduced by Alan Guth in the early 1980 seconds, explains why the universe looks smooth overall, yet still contains the seeds of structure. More recent observations, including data from Planck and the Bicep 2 experiment, suggest that during inflation there may have been subtle rotational patterns, known as B-modes, encoded in primordial gravitational waves. These faint twists in space-time could be the lingering traces of the universe's first spin, a sign that the Big Bang was not just an outward blast, but a birth with a slight twist. As the universe expanded and cooled, matter began to form step by step. First came quarks and gluons, then protons and neutrons, and later atoms. Each of these carried tiny amounts of angular momentum. When gravity eventually pulled this matter together into stars and galaxies, that ancient momentum was preserved. It's the same rule you see when a figure skater spins faster by pulling in her arms. In physics, motion doesn't appear from nothing. Rotation must come from rotation. That means the first spin, however small, had to be there from the start. Even today, astronomers may be seeing echoes of that early motion. In 2011, researchers at the Harvard-Smithsonian Center for Astrophysics analyzed more than 15,000 spiral galaxies and noticed a slight imbalance in how they rotate. While the results are still debated, this possible handedness of the universe hints that there may be an underlying order, a quiet rhythm shaping the cosmos. Dark matter may also carry this signature. Simulations from NASA's Jet Propulsion Laboratory show that dark matter halos slowly rotate over billions of years, guiding the galaxies within them like invisible whirlpools. Without that rotation, many galaxies would never hold together. So the universe seems to have been set spinning early on, and that motion still echoes through everything we see. But the deeper question remains: what started it? Physicists often point to symmetry breaking. In the earliest moments of the universe, the fundamental forces were once unified. As the universe cooled, that balance fractured. When symmetry broke, tiny imperfections appeared. According to the European Space Agency, those imperfections made structure, motion, and rotation possible. In a perfectly symmetrical universe, nothing could ever move. But introduce even the smallest imbalance, and suddenly everything can turn. We see this lack of perfect symmetry everywhere, in the way galaxies rotate, in the way atoms spin, even in the strange fact that neutrinos prefer one direction over another. Nature is not perfectly balanced, and that slight imperfection is what allows motion to exist at all. Some scientists have even tried to test whether the universe itself is rotating. In 2020, astrophysicist Lior Shamir analyzed more than 200,000 galaxies from the Sloan Digital Sky Survey and found that galaxies in one half of the sky tend to rotate differently than those in the other. His results suggest the universe may have a large-scale pattern of motion that began very early in its history. This doesn't mean the universe spins like a giant wheel. It may mean that space-time itself twisted slightly as it expanded. Even a tiny twist, stretched across billions of light years, could influence the shape of everything. To us, it feels invisible. On a cosmic scale, it could be fundamental. That's why missions like the James Webb Space Telescope are so important. Webb is already observing galaxies that formed just a few 100 million years after the Big Bang, and some of them show organized rotation far earlier than expected. This suggests the universe didn't slowly learn how to spin. It was born that way. And even at the smallest scales, spin is unavoidable. Every fundamental particle carries intrinsic spin, a built-in property described by quantum mechanics. It's not rotation in the everyday sense, but something deeper, encoded into the mathematics of reality itself. As Richard Feynman once pointed out, particles don't spin like tiny balls. They simply have spin just as they have mass. And that simple fact may trace all the way back to the very first moment the universe began to turn. So, in a very real sense, rotation wasn't something the universe picked up along the way. It was there from the start, woven into the blueprint of existence itself. When you look up at the night sky, you're not just seeing distant objects. You're seeing the inheritance of that first motion. Every spiral galaxy, every planetary orbit, every photon traveling through space traces its lineage back to that earliest cosmic turn. Without rotation, matter would never have gathered. Stars would never have ignited. Time itself would lack a rhythm to follow. Motion is not a side effect of the universe. It is its pulse. And while we may never fully uncover what sparked that very first spin, the evidence keeps quietly pointing to the same idea. It has always been there, steady and unseen, written into everything we can observe. As ESA cosmologist Jean Tabot once put it, the universe remembers not through words, but through patterns of light. And within those patterns is the faint imprint of the first motion, a twist older than time itself. So when we ask, who set the universe spinning, the most honest answer may be this: the universe never learned how to move. It began already in motion. The spin was not created later. It was passed down. Take a slow breath. The atoms inside your body are still turning with that original impulse. From the smallest electron to the vast rotation of the Milky Way, the same motion continues, uninterrupted, for nearly 13.8 billion years. We are not separate from it. We are part of it. And as this story moves forward, we arrive naturally at the next question. If rotation shaped the birth of the universe, could it also be the reason life itself exists? That's where we turn now. Part 3. Did spinning make life possible? Without rotation, Earth would be a quiet place. No dawn, no dusk, no changing skies. Just one side locked in darkness and cold, the other scorched beneath endless sunlight. A silent world drifting through space. But because Earth spins, the planet lives. Every sunrise, every ocean tide, every breath of wind flows from the same ancient motion that began 4.5 billion years ago. The Earth's rotation isn't just movement. It's a working system, a fragile balance that supports everything we call life. From the magnetic field that protects us from cosmic radiation to the temperature cycles that sustain oceans and clouds, rotation shapes our world in ways both obvious and hidden. According to NASA's Goddard Space Flight Center, Earth rotates near the equator at roughly 1,037 miles per hour, completing one full turn every 23 hours, 56 minutes, and 4 seconds. This period, known as a sidereal day, sets the tempo for nearly every biological and environmental process on the planet. Plants, animals, oceans, and even microscopic life all move in step with this rhythm. It's like an unseen metronome ticking beneath everything that lives. The most immediate result of Earth's spin is the cycle of day and night. Rotation spreads sunlight across the planet, creating temperature differences that drive winds, ocean currents, and weather. Without this steady turning, one hemisphere would burn under constant daylight, while the other froze in permanent darkness. The dividing line between them would be violent and unstable, a hostile zone where life could barely survive. Because the planet rotates, sunlight is shared just evenly enough to allow stable climates and habitable regions to exist. Rotation also plays a crucial role in maintaining Earth's magnetic field. Deep below the surface, the planet's molten iron core moves and flows, generating a powerful magnetic dynamo. As described by NASA's magnetospheric multiscale mission, this motion creates the magnetic field that shields Earth from the solar wind, a constant stream of charged particles released by the sunday. Without that shield, our atmosphere would slowly be stripped away, much like what happened on Mars. Mars still rotates once every 24.6 hours, similar to Earth, but its smaller core cooled long ago. When its internal motion faded, its magnetic field collapsed, and the planet lost much of its atmosphere, becoming the cold, dry world we see today. Here on Earth, the magnetic field also gives rise to the auroras, those glowing curtains of light near the poles. They're more than beautiful displays. They're visible evidence of protection, showing where charged solar particles interact with magnetic field lines. Each aurora is a reminder that Earth's rotation continues to power an invisible shield around the planet. The influence of spin doesn't end there. Rotation also shapes the behavior of the atmosphere itself. As Earth turns, air moving between the equator and the poles curves, a phenomenon known as the Coriolis effect. This bending motion organizes winds and ocean currents, giving rise to jet streams, trade winds, and rotating storms. It's why hurricanes spiral, why weather systems move the way they do, and why heat is carried across the globe. Without the Coriolis effect, weather patterns would collapse into disorder, storms would lose structure, and climates would fail to stabilize. A planet's rotation speed directly affects its climate. Simulations by NASA's Global Modeling and Assimilation Office show that worlds with slower rotation tend to overheat on one side and freeze on the other, while faster spinning planets can develop extreme winds and unstable atmospheres. Earth's roughly 24-hour day sits in a narrow sweet spot, long enough to distribute heat, short enough to prevent runaway extremes. That balance is one of the quiet reasons life thrives here. Rotation also shaped life from the inside out. Living organisms evolved internal clocks, circadian rhythms tuned to Earth's spin. Research published through the National Center for Biotechnology Information shows that nearly every cell on the planet carries a molecular clock synchronized to this daily cycle. These rhythms guide when plants open their leaves, when animals rest or hunt, and when humans sleep and wake. If Earth suddenly stopped rotating, this biological harmony would collapse. Light and darkness would lose their regular pattern, and life would struggle to adapt. Spin even played a role in how the moon became our companion. Early in Earth's history, a Mars-sized body called Theia collided with the young planet. The debris from that impact eventually formed the moon, and the collision dramatically increased Earth's rotation rate. Over billions of years, the moon's gravity has slowly slowed that spin, stretching Earth's day from about 6 hours to the 24-hour cycle we know now. At the same time, the moon stabilizes Earth's axial tilt, preventing extreme climate swings. Data from the Gaia mission shows that this stability is crucial for long-term habitability. Planets that wobble too much often experience chaotic climate shifts. Earth and the moon now exist in a slow gravitational exchange. Ocean tides, shaped by the moon, also act as a brake on Earth's rotation, slowing it by about 1.7 milliseconds per century, according to NASA's Jet Propulsion Laboratory. Even the length of our day, the basic rhythm of life, is changing, though so slowly we barely notice. Looking beyond Earth, rotation plays a similar role across the solar system. Jupiter spins once every 9 hours and 56 minutes, making it the fastest rotating planet. That speed drives immense jet streams and storms, including the Great Red Spot, a hurricane larger than Earth that has persisted for centuries. On the opposite extreme, Venus rotates extremely slowly and backward, taking 243 Earth days to complete a single turn. It has almost no magnetic field, and its thick carbon dioxide atmosphere traps heat, creating a runaway greenhouse effect that makes it the hottest planet in the solar system. The contrast is stark. Too fast, and chaos dominates. Too slow, and protection disappears. Mars offers another lesson. Its day is only about 40 minutes longer than Earth's, but as its core cooled and stopped churning, its magnetic field faded. Solar radiation stripped away much of its atmosphere and water, leaving behind faint magnetic traces in the crust, ghostly remnants of a world that once had the motion needed to stay alive. Rotation, then, is not optional for habitability. It's essential. In 2023, observations from the James Webb Space Telescope of exoplanets, such as WASP-3 9b and TRAPPIST-1e, showed that planets with detectable spin or atmospheric circulation tend to have more stable temperature distributions. Chemical balance. Without rotation, energy either builds up or escapes too quickly, creating environments that struggle to support life. As NASA's exoplanet exploration program summarizes, rotation plays a defining role in shaping climate and determining whether a planet can remain habitable. Rotation may also be closely tied to magnetic protection on worlds far beyond our own. A 2021 study from the Harvard-Smithsonian Center for Astrophysics pointed out that exoplanets with faster rotation tend to keep their metallic cores molten for longer periods of time. That molten motion sustains magnetic fields, and those fields act as shields, preserving atmospheres and increasing the chances that liquid water can exist on the surface. And where liquid water can persist, life has a better chance to take hold. So when we ask whether spinning made life possible, the evidence leans clearly toward yes. Rotation shapes a planet's day length, its temperature differences, its atmosphere, its weather systems, and its magnetic protection. Life, it seems, doesn't survive in spite of motion, but because of it. Earth's rotation speed hasn't always been what it is today. Over billions of years, it has slowly changed. Yet its influence continues to ripple through time. It governs the rhythm of tides, the spread of forests, the long migrations of animals across continents. It even defines how we experience time itself, not as an abstract idea, but as the physical turning of the ground beneath our feet. As astrophysicist Neil deGrasse Tyson once said, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Take a quiet moment. Listen to that turning. Every rotation carries the memory of 4.5 billion years of balance and motion. If Earth were to stop spinning tomorrow, the oceans would rush toward the poles, the atmosphere would collapse into turmoil, and the planet would slowly lose its breath. But tonight, as it turns gently beneath you, everything still works, smoothly, silently, continuously. So it may not be an exaggeration to say that Earth's rotation is the quiet architect of life. The same cosmic motion that once gathered dust into a planet now spins that planet into mornings, into wind, into rain, into you. And as we move deeper into this journey, we follow that rotation outward to a place where spinning no longer just shapes life, but begins to bend something even stranger. Because beyond a certain limit, rotation doesn't simply move matter, it starts to twist time itself. That's where our next chapter begins. Part 4. Can rotation bend time itself? When rotation reaches its extremes, it stops feeling like motion and starts behaving like distortion. At very high speeds, turning objects don't just travel through space, they begin to pull on time. Einstein's general theory of relativity, published in 1915, revealed that gravity and motion are deeply connected, both expressions of how mass and energy curve space-time. The greater the mass, or the faster the spin, the more that surrounding space-time is twisted. This effect, known as frame dragging, is one of the most subtle and beautifully confirmed predictions in all of physics. Imagine space-time as a calm, glassy lake. When a massive object spins, whether it's Earth or a black hole, it stirs that lake, creating tiny vortices in the flow of space and time. Within those swirls, even time itself begins to curve. NASA physicist Francis Everett, who led the Gravity Probe B experiment, described it this way: as Earth rotates, it drags space-time around with it, like a spinning ball twisting the honey it's submerged in. Launched in 2004, Gravity Probe B used 4 ultra-precise gyroscopes orbiting about 400 miles above Earth to measure this effect. After a year of data, NASA confirmed that Earth's rotation drags space-time by roughly 0.000011 degrees per year. The effect is tiny, but it matches Einstein's predictions with astonishing accuracy. Even our calmly spinning planet is capable of bending time. Now imagine something far more extreme: a rotation billions of times faster, wrapped in a gravitational field billions of times stronger. That's the realm of neutron stars. When a massive star collapses at the end of its life, its core compresses so intensely that protons and electrons merge into neutrons. The result is an object only about 12 miles wide, yet more massive than our Sunday. To conserve angular momentum, these remnants spin at incredible speeds, sometimes hundreds of times per second. We observe them as pulsars, flashing beams of radiation that sweep through space like cosmic lighthouses. Their rotation generates the strongest magnetic fields known and twists space-time so severely that even light struggles to move in straight lines. NASA's NICER instrument aboard the International Space Station has mapped these effects, revealing that time near a pulsar runs more slowly than it does on Earth. The faster the spin, the stronger the slowdown. This isn't science fiction. It's gravitational time dilation, a direct outcome of Einstein's equations. Near massive, rapidly spinning objects, space-time itself is dragged into motion. Nothing nearby can remain truly still. The most extreme examples of this come from rotating black holes, known as Kerr black holes, named after mathematician Roy Kerr, who solved Einstein's equations for spinning black holes in 1963. Unlike non-rotating black holes, which simply pull inward, Kerr black holes twist space-time violently around their axis. Near the event horizon, that twisting approaches the speed of light. The region just outside the horizon, called the ergosphere, is where frame dragging becomes overwhelming. Inside it, nothing can stay stationary relative to the distant universe. Every particle, every photon is forced to rotate with the black hole, as if space itself has become a vast, invisible whirlpool. In 2021, observations from NASA's Chandra X-ray Observatory showed matter spiraling around the black hole at the center of galaxy M87, confirming that it spins near the theoretical limit. In that region, time behaves very differently. If it were somehow possible to hover safely near the ergosphere, your clock would tick far more slowly than clocks on Earth. Minutes for you could mean hours elsewhere. Einstein described this as the warping of time, the unavoidable result of motion and gravity acting together. The Event Horizon Telescope offered striking confirmation of this idea. In 2019, it released the first image of a black hole's shadow, and in 2022, it revealed Sagittarius A*, the supermassive black hole at the center of our galaxy. The glowing ring in those images isn't light from the black hole itself, but from matter spiraling around it, light bent, delayed, and distorted by curved space-time. Those arcs are visual proof that rotation and gravity can bend not just light, but time. This bending of time isn't limited to distant cosmic monsters. Even satellites orbiting Earth experience it. The GPS system must constantly correct for time dilation caused by both gravity and motion. Without those corrections, GPS clocks would drift by about 38 microseconds each day, enough to throw navigation off by miles. Even here, in what feels like calm space, time is already being gently reshaped. In theoretical models of spinning black holes, the mathematics becomes almost surreal. Extreme rotation allows solutions where paths loop back on themselves in time, known as closed time-like curves. Whether such paths can exist in reality remains uncertain, but they naturally arise from Einstein's equations. In these environments, the usual ideas of past and future begin to blur. The James Webb Space Telescope now observes the accretion disks of distant quasars, galaxies powered by supermassive rotating black holes. Webb's infrared measurements show light stretched and redshifted, clear signs that time flows more slowly near those spinning giants. Some of that light has traveled for over 13 billion years before reaching us. In a very real sense, we're watching time itself stretched across the universe. Rotation, it turns out, doesn't just shape matter, it shapes how time flows. From Earth's gentle spin to the violent cores of galaxies, motion sculpts both space and time. What we call now depends on where you are and how fast space-time is turning around you. Even light, the fastest thing we know, is forced to bend and linger near spinning masses. NASA's NuSTAR and XMM Newton missions have captured X-ray echoes around black holes, light briefly trapped in orbit before escaping. In those echoes, time stretches, measurable and real. It raises a final, unsettling thought. Could the universe itself be twisting time on the largest scales? Current data from ESA's Planck mission shows no strong evidence for a global cosmic spin. But the question isn't fully closed. Even a faint, ancient twist across billions of light years might leave subtle fingerprints in the polarization of old light. As physicist Kip Thorne once explained, near a spinning black hole, the future of one observer can become the past of another. In a universe built on rotation, time itself may never be as simple as it seems. Rotation doesn't merely change paths through space. It changes the very rhythm of reality. It reshapes the sequence of events, subtly rewriting the way existence unfolds. Imagine for a moment that time is not a linear river, as we usually think, but a delicate fabric woven from motion itself. Every spin, every orbit, every oscillation tugs at this fabric, stretching some threads, compressing others. And although this idea may sound abstract or even mystical, it is not metaphorical. It is measured, observed, and confirmed in the laboratory, in the skies above us, and even in the satellites that circle our planet with silent precision. Atomic clocks, the most precise timekeepers ever built by humanity, prove it. When scientists place identical clocks on airplanes, high-altitude balloons, or satellites in orbit, their readings diverge ever so slightly. The clock moving fastest or sitting deepest in a gravitational well ticks slower than its stationary counterpart. This is not an optical illusion, nor a trick of perception. It is time itself stretching, bending, and yielding to motion and gravity. Faster motion slows time. Stronger gravity deepens this effect. This principle, born from Einstein's theory of relativity, is as real as the ground beneath our feet. It is a reminder that the universe does not merely unfold in time. Motion, spin, and energy actively shape it. Consider the world around you. The Earth rotates beneath your feet, imperceptibly yet inexorably. The sun pulls on our planet with a gravitational embrace that guides the rhythm of seasons. Our galaxy, the Milky Way, drifts and rotates, carrying the sun and billions of other stars along its vast spiral arms. Every second you live is tied to these motions. Your heartbeat, the oscillation of atoms in a clock, the rotation of the Earth, all are part of an intricate, interlocking system that defines the very pace of existence. But if rotation can shape time, the question naturally arises: can time influence rotation in return? It's a paradoxical idea, yet one that sits at the heart of modern physics. Every second of life depends on motion. A clock ticks because something vibrates in a predictable pattern. Your heart beats because muscles contract rhythmically. Even electrons, the fundamental carriers of charge, possess a property known as spin, a form of angular momentum that defines their behavior and contributes to the structure of atoms. On a cosmic scale, The Earth completes a full rotation every 24 hours, and that very motion subtly bends the flow of time. Clocks at the equator, where the surface moves fastest, run slightly slower than those at the poles, not due to weather or altitude, but because of the underlying principles of relativity. Einstein's insight was revolutionary. Motion and gravity stretch time. It is a tangible, measurable phenomenon. And once you see time through this lens, the universe becomes a more interconnected and rhythmic place. Motion does not merely happen within time. Motion creates time. Every orbit, every spin, every oscillation contributes to the flow of seconds, minutes, and hours as we perceive them. To understand the origin of spin, scientists often turn to atomic clocks, where electrons shift between precisely defined energy states. Each transition releases radiation at an exact frequency determined by the cesium-133 atom, which defines the length of 1 second in our modern timekeeping system. At this scale, time is no longer tied to the motion of planets or stars. Time emerges from the intrinsic spin of matter itself, from the smallest quantum properties that govern how particles behave, how atoms form, and how the building blocks of reality interact. Spin, in this sense, is not a literal rotation. It is a fundamental property of existence, woven into the laws that dictate the universe. On larger scales, the rhythm of the cosmos becomes tangible. Planetary spins define days, orbital paths define years, and galactic rotations define cosmic eras. Our planet is gradually slowing under the tidal influence of the moon. Milliseconds are added to our days over centuries, necessitating leap seconds to keep our clocks in harmony with the natural rhythm of the cosmos. Every modern GPS signal, every satellite communication, every timing-dependent system relies on equations that account for Earth's rotation, gravity, and relativistic effects. Without these corrections, navigational errors would accumulate rapidly, throwing spacecraft, planes, and even cell phone signals off course. Timekeeping, therefore, is inseparable from the motion of celestial bodies. Where, then, did spin originate? Astronomers trace it to angular momentum, a fundamental quantity that nature never loses. During the birth of the solar system, a vast cloud of gas collapsed under gravity. As it contracted, it began to rotate faster, conserving angular momentum. This primordial motion was distributed among the forming sun, planets, and moons. Today, these celestial bodies continue to spin almost unimpeded, because in the near-frictionless vacuum of space, motion is remarkably persistent. A planet, a star, a galaxy can spin for billions of years with little to slow it. The pattern repeats at every scale. Atomic spin dictates the ticking of seconds. Planetary spin dictates the length of a day. Galactic rotation dictates the timeline of entire cosmic eras. The Milky Way itself rotates once every 230 million years, carrying the Sun, our solar system, and all the stars of its spiral arms in a vast cosmic dance. Even the Sun has its own spin, twisting at varying rates across its surface, and generating magnetic fields that drive solar storms capable of reaching Earth. Spin is never passive. It is the engine of cosmic cycles, the sculptor of magnetic fields, the regulator of time itself. Einstein's equations tie it all together. Energy, momentum, including angular momentum, determines how space-time curves. Remove spin, and space-time simplifies. Introduce spin, and time begins to bend, warp, and flow in intricate patterns. From the laboratory to the galaxy, from atomic clocks to interstellar rotations, the same principles apply. Even light, traveling across billions of light years, is subtly influenced by the rotation of massive objects it passes. Time and spin are intertwined, locked in a cosmic embrace that stretches from the quantum to the galactic scale. Observations from the James Webb Space Telescope have pushed this understanding even further. When it gazes upon galaxies whose light has traveled over 13 billion years to reach us, we see rotation already in place. Angular momentum was present nearly from the beginning of the universe. From the first stars to the largest galaxies, spin has been a fundamental player, helping to shape time, structure, and evolution. Time, therefore, did not precede motion. Spin helped give time its direction, its rhythm, its pulse. And yet, as humans, we naturally ask, who controls it? Who guides the cosmic dance? The most honest answer physics offers is that no one does. The universe governs itself through immutable laws. Motion is conserved. Balance is maintained. What slows in one region accelerates in another. The same rules apply from the tiniest particle to the largest galaxy. The universe is a self-regulating system, an immense clockwork in which every rotation, every orbit, every oscillation contributes to a harmony that is both orderly and awe-inspiring. Consider the implications. Every heartbeat, every breath, every second of your life is intertwined with the motion of planets and stars. Even our artificial constructs, our clocks, our satellites, our instruments must adapt to the rhythms of the cosmos. We have built precision timekeeping not to overcome nature, but to sync with it, to measure the subtle dance of spin and gravity that defines reality. Leap seconds are added, atomic clocks are calibrated, satellites are corrected, all to align human perception with the universe's inherent motion. This interconnectedness stretches further. The spin of particles governs chemistry. The rotation of planets influences climates and tides. The rotation of galaxies shapes the evolution of stars and the distribution of matter. Every scale of existence is connected by angular momentum, by the laws of motion, and by the flow of time that these motions create. The cosmic web is alive with movement, and through that movement, time itself emerges, flows, and bends. Ultimately, the story of spin is a story of balance, from the quantum to the galactic, from atoms to galaxies. The universe runs on consistent principles. No external force dictates it. No conscious entity guides it. It simply is. Spin is preserved. Motion is conserved. And time, in turn, is measured, defined, and molded by these motions. The universe is both self-aware and self-sustaining, a perpetual dance where motion and time are inseparable partners. So, as you pause and reflect, consider your place in this cosmic choreography. Every second you experience is a testament to ancient spins, enduring orbits and rotations that began billions of years ago. The universe runs on balance, a harmony that transcends human understanding, a rhythm that defines existence itself. Motion creates time. Time governs motion, and together they weave the tapestry of reality. The laws of physics, silent yet exact, ensure that the dance continues unceasing, eternal, and profoundly beautiful. There is no master clock ticking behind reality, no hidden mechanism counting seconds in the dark. Time does not arrive from the outside. It emerges from motion itself. Spin is the universe's internal gyroscope, a quiet stabilizer, a built-in sense of orientation that keeps everything aligned without instruction. From the smallest particles to the widest galaxies, the same rule applies. When systems slow, collide, or break apart, their angular momentum does not disappear. It moves elsewhere. It transfers. It continues. The cosmic rhythm never stops. It only changes hands. So when we ask who controls the spin, the universe answers without words. No one needs to. Motion sustains itself. Take a breath. The atoms inside you are turning. The earth beneath you is rotating. The moon is circling. The Milky Way is slowly spiraling through space. You are not watching this motion. You are inside it. Every heartbeat you feel is a fraction of a rhythm that began long before clocks, calendars, or even light itself. And as that rhythm continues, another question rises. Not suddenly, slowly, almost inevitably. If the universe depends on balance, what happens when that balance breaks? Part 6. Did the universe begin because symmetry was broken? Imagine a universe in perfect balance. No direction preferred over another. No difference between left and right. No past or future. Nothing would ever change. No stars would form. No atoms would bind. No time would pass. Perfection is motionless. But the universe we inhabit is not perfect. It never was. Everything we see exists because something, somewhere, slipped out of balance. In physics, symmetry means that the laws of nature behave the same everywhere, in every direction, and for every observer. When symmetry holds completely, nothing has a reason to evolve. But when symmetry breaks, even by the smallest amount, change becomes possible. The earliest universe was hot, dense, and astonishingly uniform. According to modern physics, all fundamental forces were once unified. Gravity, electromagnetism, and the nuclear forces were indistinguishable. But as the universe expanded and cooled, that unity fractured. This process is known as spontaneous symmetry breaking. It did not require an external cause. It happened because perfect balance cannot survive expansion. The Planck satellite mapped the cosmic microwave background, the faint afterglow left behind when the universe became transparent. What it found was remarkable. The early universe was smooth, but not perfectly so. Tiny variations in temperature, no more than 1 part in 100,000, marked the first cracks in symmetry. Those cracks mattered. Where density was slightly higher, gravity had something to work with. Matter began to clump. Over hundreds of millions of years, those faint irregularities grew into galaxies, stars, and planets. Without them, the universe would remain a thin, uniform fog. No structure, no complexity, no observers. Even the existence of matter itself depends on imbalance. In the early universe, matter and antimatter were produced in nearly equal amounts. For every particle of matter, there was a matching particle of antimatter. When they met, they annihilated into energy. But the balance was not exact. For every billion pairs, one extra particle of matter remained. That single survivor, multiplied across the universe, became everything we know. This asymmetry is called baryon asymmetry. It is the reason galaxies exist instead of pure radiation. In 1964, physicists James Cronin and Val Fitch discovered that the laws of physics treat matter and antimatter slightly differently. Their experiments revealed a phenomenon known as CP violation. This tiny preference for matter over antimatter shattered the idea of perfect symmetry and earned them the Nobel Prize. Without this imbalance, the universe would contain no atoms, no chemistry, no life. At CERN, scientists continue to study how symmetry breaks at the deepest levels. The Higgs field plays a central role. When the universe cooled below a critical temperature, the Higgs field settled into a non-zero value everywhere in space. That single event gave particles mass and locked in differences that allowed structure to persist. It was not violent, it was inevitable. Like a perfectly balanced pencil standing on its tip, the universe could not remain symmetric forever. Eventually, it had to fall in some direction. Time itself may have chosen its arrow in the same way. In the earliest moments, time may not have preferred forward over backward, but a tiny fluctuation, perhaps linked to entropy or quantum randomness, nudged it in one direction. Once chosen, the path could not be undone. Physicist Sean Carroll describes the arrow of time as a memory of low entropy at the beginning of the universe. We experience time flowing because the universe began in an unlikely, imbalanced state. Even gravity depends on broken symmetry. If matter were distributed perfectly evenly, gravitational forces would cancel out. Nothing would move. But because the universe was slightly uneven, gravity could act. Matter fell inward, forming stars and galaxies. On smaller scales, asymmetry appears again and again. Neutrinos prefer a single-handedness. Biological molecules come in left-handed and right-handed forms. But life on Earth uses almost exclusively one orientation. Even galaxies show a preference in rotational direction. These biases may trace back to the earliest moments of symmetry breaking. Some studies suggest that polarized ultraviolet light from early stars influenced the chemistry of life, destroying one molecular orientation more than the other. If true, then even biology carries a memory of cosmic imbalance. The cosmic microwave background itself may preserve this history. Subtle polarization patterns hint at primordial gravitational waves, ripples from the universe's earliest expansion. If confirmed, they would be direct evidence that the universe's first act was to break symmetry. Perfection is elegant, but sterile. Imperfection creates. When we observe the universe through telescopes like the James Webb Space Telescope, we are not just seeing distant objects, we are seeing the fossil record of imbalance. The moment when stillness gave way to motion. You exist because symmetry failed. Every atom in your body survived by the smallest margin imaginable. One extra particle in a billion. That imbalance has been preserved for over 13 billion years, carried forward through stars, planets, and living cells. So yes, the universe began because symmetry broke. Motion followed. Time emerged. And from that first imperfection came everything that spins, shines, and breathes, which leads us naturally to the next mystery. If galaxies spin faster than gravity alone allows, what keeps them together? Part 7. What holds galaxies together when they spin too fast to exist? Galaxies rotate at impossible speeds. Stars on their outer edges move so fast that, according to classical physics, they should escape into space. Like sparks flying from a spinning wheel, galaxies should tear themselves apart, but they do not. Something unseen is holding them together. Astronomers call it dark matter. Dark matter does not emit light. It does not reflect light. It does not absorb light. It does not form atoms or molecules. It does not collide or clump the way ordinary matter does. But it has mass. And it pulls? The mystery first appeared in the 1930 seconds, when Swiss astronomer Fritz Zwicky studied the Coma Cluster, a massive collection of galaxies hundreds of millions of light-years away. Zwicky measured how fast the galaxies were moving and found that their visible matter was nowhere near enough to hold the cluster together. By all known laws, it should have dispersed long ago. Zwicky proposed that an unseen mass must exist, outweighing the visible matter. He called it dark matter. At the time, the idea was largely ignored. Decades later, the evidence became impossible to dismiss. In the 1970 seconds, astronomer Vera Rubin measured the rotation curves of spiral galaxies. She found something unexpected. Stars far from galactic centers were moving just as fast as those near the core. According to Newtonian gravity, orbital speeds should decrease with distance, but they did not. The rotation curves were flat. This meant that mass was distributed far beyond what telescopes could see. Galaxies were embedded in massive, invisible halos, extending well past their visible edges. NASA now estimates that dark matter makes up about 85% of all matter in the universe, roughly 5 times more than everything we can see. Each galaxy sits inside a dark matter halo. These halos act as gravitational scaffolding, holding stars and gas together as they spin. Without dark matter, galaxies like the Milky Way would unravel in a few million years. Dark matter also explains gravitational lensing, where light from distant galaxies bends around invisible mass. It shapes the cosmic web, guiding the formation of large-scale structure. Simulations show that without dark matter, the universe would look nothing like it does today. Yet despite its influence, dark matter remains elusive. It does not interact with electromagnetic radiation. It passes through ordinary matter almost without notice. Detectors deep underground search for faint signals, but so far, dark matter has revealed itself only through gravity. Some theories suggest dark matter particles. Others propose modifications to gravity itself. But the evidence for unseen mass remains overwhelming. Once again, imbalance shapes reality. Galaxies spin faster than they should. Something unseen compensates. Balance is restored, not by symmetry, but by hidden mass. From broken symmetry to invisible matter, the universe seems to thrive on what cannot be seen directly. Motion persists, structure survives, time continues to flow. And as galaxies spin in the dark, another question waits beyond the edge of understanding. If most of the universe is invisible, what else might be shaping reality without leaving a trace of light? Simulations from NASA's Goddard Space Flight Center reveal a subtle truth. Dark matter is the invisible glue that allows galaxies to exist at all. It is not a suggestion or a theory whispered into existence. It is a framework that holds the cosmos together, allowing stars to cluster, galaxies to spin, and the universe to develop structure across billions of years. Without it, matter would drift apart, spread thinly, and never gather into the luminous islands we see scattered across the night sky. The European Space Agency has also contributed to this story, observing the cosmic web of unseen matter through the phenomenon of gravitational lensing, the bending of light by massive objects. When photons from distant galaxies pass near clusters rich with dark matter, the invisible mass warps space-time itself, magnifying and distorting the background light into arcs and streaks. This effect is not an illusion. It is a visual signature of a hidden force, shaping reality while remaining beyond direct perception. The Euclid mission, launched in 2023, takes this investigation to a new level. Its aim is ambitious: to map these gravitational distortions across billions of galaxies, creating the most detailed three-dimensional chart of dark matter ever constructed. Even before Euclid, the Hubble Space Telescope gave us stunning glimpses of this invisible cosmic architecture. In 2006, Hubble captured the Bullet Cluster, a dramatic collision between two galaxy clusters. X-ray images from NASA's Chandra Observatory showed that the hot gas, composed of ordinary matter, lagged behind the collision. But when scientists mapped the total mass using gravitational lensing, they discovered that most of the mass lay ahead, separated from the visible matter. Here was proof. The majority of the universe's mass is unseen, independent, and profoundly mysterious. Dark matter interacts only through gravity and possibly the weak nuclear force, but it does not interact with light. It does not shine, it does not reflect, it does not absorb. It is, by all accounts, imperceptible, yet its influence is ubiquitous. Leading candidates for dark matter include WIMPs, weakly interacting massive particles, and axions, hypothetical particles predicted by extensions of the Standard Model of Physics. Experiments deep underground, such as Xenon NT in Italy and Lux Zeppelin in South Dakota, attempt to detect the rare collisions of these particles with atomic nuclei. Shielded from cosmic rays, these detectors wait patiently in silence, like archaeologists uncovering clues to a hidden past. So far, the search has yielded no confirmed detection, but the quest continues, quietly, methodically, year after year. Meanwhile, NASA's Fermi Gamma Ray Space Telescope searches for subtle signatures of dark matter annihilation in galactic centers. JWST, the James Webb Space Telescope, peers even farther, examining the faint structures of galaxies less than 400 million years after the Big Bang. Remarkably, even at this young cosmic age, galaxies already show stable rotation. The conclusion is clear: dark matter halos must have existed almost immediately, guiding the early universe's evolution. Scientists at the Astrobiology Institute of NASA note, dark matter must have formed early, shaping the universe long before the first stars ignited. With that is in first of eye. On the largest scales, dark matter dictates not only how galaxies rotate, but how the universe itself evolves. Computational projects like NASA's Illustris and Eagle simulations make this tangible. When dark matter is removed from the equation, matter remains evenly spread, incapable of clumping together. Galaxies fail to form. Stars never gather. The universe becomes an empty, diffuse sea, lacking the complexity that defines the cosmos as we experience it. Dark matter provides invisible scaffolding, a framework upon which visible matter condenses, spins, and shines. Astrophysicist Neil deGrasse Tyson once described dark matter as the greatest cosmic mystery of our time, a shadow universe holding ours in its invisible grip. And yet, it leaves traces everywhere. It shapes the structure of galaxy clusters, directs cosmic filaments, and even influences the expansion of the universe itself. While dark matter does not emit radiation, its gravitational presence slows the outward march of the universe, competing with the repulsive force of dark energy. This delicate tug-of-war between invisible attraction and cosmic acceleration defines the large-scale structure of existence. Consider the Milky Way, our own galactic home. The Sun orbits the galactic center at roughly 514,000 miles per hour, completing one rotation every 230 million years. By classical physics alone, the galaxy should have torn itself apart long ago. Stars on the periphery should have drifted away, scattered into the void, but they do not. Encasing the Milky Way is a vast dark matter halo, extending perhaps 200,000 light-years beyond the visible disk, providing the extra gravitational mass necessary to keep the galaxy intact. The balance between spin and gravity is astonishingly precise. Slightly less dark matter, and galaxies would disperse. Slightly more, and they would collapse under their own weight. According to the Planck satellite, the universe is composed of approximately 68% dark energy, 27% dark matter, and only 5% ordinary matter. Every planet, every star, every person accounts for only a fraction of what truly exists. The visible universe is a mere stage upon which the bulk of reality, the invisible majority, performs its silent work. What makes dark matter so perplexing is that it defies direct measurement. We can see its influence, map its distribution, and simulate its effects with astonishing precision, but its identity remains hidden. Some physicists speculate that our understanding of gravity itself may require adjustment. Theories such as modified Newtonian dynamics, MONDA, or tensor vector scalar gravity, TDE, attempt to explain galaxy rotation without invoking dark matter, but none has matched the consistency of the dark matter hypothesis. New missions promise to illuminate the shadows. Euclid and NASA's Nancy Grace Roman Space Telescope will collaborate to map billions of galaxies, tracing the evolution of dark matter across 13 billion years of cosmic history. JWST adds its own insights, observing the earliest galaxies to determine whether dark matter behaved consistently in the universe's infancy. If early galactic formation aligns with current models, it will confirm that dark matter's invisible hand has always guided cosmic structure. It is strange to consider that the galaxies above us, the clusters and filaments spanning millions of light years, are held together by something we cannot see, touch, or directly measure. Yet, it is this invisible force that orchestrates the cosmic symphony, keeping the universe in tune. Without it, stars would scatter, galaxies would unravel, and the universe would lose its form. Dark matter is the quiet architect, a framework made not of photons but of gravitational stability. Take a deep breath. Every star you have ever glimpsed, every galaxy drifting across your telescope exists on the foundation of something invisible. You live within a universe held together by shadows, forces, acting without being seen, guiding the motion of everything that spins, from electrons to entire galactic disks. And as we follow that invisible hand through the cosmos, we begin to notice something even stranger, a force that opposes the gravitational embrace of dark matter, a force that accelerates the expansion of the universe rather than slowing it, a force that stretches the fabric of space itself. This is dark energy, the other half of the cosmic puzzle, the unseen influence dictating the ultimate fate of everything we know. Whereas dark matter binds and scaffolds, dark energy drives apart, stretching galaxies away from each other with increasing speed. Its discovery, first observed through distant supernovae in the late 1990 seconds, revealed a universe that is not slowing down, as expected, but accelerating. The balance between gravity and expansion is now tilted, and the cosmos seems to have a preference for growth, for spreading, for vast emptiness. Dark energy constitutes nearly 70% of the universe's total content, dwarfing dark matter and ordinary matter alike. It is both the engine and the mystery, invisible yet dominant, pervasive yet undetectable through conventional means. Unlike dark matter, which exerts a pull, dark energy pushes, and as the universe ages, this pushing becomes ever more pronounced, altering the ultimate destiny of galaxies, stars, and even the atoms that make up you. Every observation, every simulation, every faint signal we can measure points to a staggering truth. The universe is largely unseen, its motions dictated by invisible matter and energy. The galaxies we admire, the cosmic filaments we map, the spiral arms of the Milky Way, they exist because of forces that do not emit light, forces that we cannot feel, forces that only manifest through their effect on everything else. So, pause for a moment. Reflect on this. The universe is spinning, stretching, and evolving around you, held together and shaped by forces you cannot directly perceive. Dark matter and dark energy form the invisible scaffolding and the expanding void, crafting the structure and destiny of all that exists. The cosmos, in its entirety, is a dance of shadows, a symphony of invisible hands, guiding the rotation, motion, and flow of time itself. And as we peer further into the depths, tracing these unseen threads, one question looms larger than any other. If the universe is governed by such subtle and hidden forces, how much of reality remains beyond our senses? And what else might we discover if we learn to read the patterns of the invisible? The story of dark matter and dark energy is not just a story of what exists, it is a story of balance, motion, and the invisible rules that sculpt everything we know. From the rotation of galaxies to the expansion of space, from the spin of electrons to the drift of cosmic filaments, the universe is alive with hidden forces. It spins, it stretches, it persists, all guided by the unseen. Every telescope, every probe, every mission is a small step toward illuminating this shadow universe. But for now, remember, the stars above, the galaxies far away, even the earth beneath your feet, all exist because of what you cannot see. In every motion, in every orbit, in every cosmic rotation, the invisible continues to hold sway. Take another slow breath. You are part of this vast, unseen architecture. You are cradled within a universe whose greatest truths are hidden, yet whose effects resonate through every atom, every star, every heartbeat. Part 8. Does the universe's spin decide the direction of life? If dark matter holds galaxies together, could it also have shaped life itself, even down to the way molecules twist? Could the same invisible forces that guide the spin of stars and galaxies have left a subtle mark on the very chemistry of life? This is the question we explore now. Every living thing on Earth is slightly twisted. Your DNA coils to the right, forming elegant double helices that encode your entire being. The amino acids, the building blocks of proteins, twist to the left. This one-sidedness, known as chirality, is one of the deepest mysteries in biology. It reveals that life, down to its smallest components, has a preferred direction, a bias, a spin. In chemistry, chirality simply means handedness. Like your left and right hands, some molecules exist as mirror images that cannot be perfectly superimposed. In most chemical reactions, both left-handed and right-handed versions form equally. But in life, only one version is ever chosen. DNA and RNA twist to the right. Proteins twist from left-handed amino acids. It's as if, long ago, life made a choice and has followed that spin ever since. Why? Scientists have long debated this. If chemistry alone produces both options equally, something outside of biology must have nudged life toward one. One clue comes from the light of ancient stars. Light can be polarized, meaning its waves oscillate more strongly in one direction. In the early universe, massive young stars emitted intense ultraviolet light. As this light passed through magnetic dust clouds, it became circularly polarized, spinning slightly in one direction. According to research from NASA's Astrobiology Institute, this polarized light may have selectively destroyed one form of amino acid over the other. Over millions of years, this tiny preference could have nudged prebiotic chemistry toward a single-handedness, eventually determining the orientation of life itself. Evidence comes closer to home as well. The European Space Agency's Rosetta mission landed on Comet 67P in 2014 and detected complex organic molecules, including amino acid precursors. Some of these molecules were already slightly biased in their handedness. This suggests that the direction of life's molecules may have been written into chemistry before life even formed on Earth. Meteorites tell a similar story. The Murchison meteorite, which fell in Australia in 1969, contained over 70 amino acids. Scientists later discovered a subtle excess of left-handed forms the same handedness that life on Earth uses. NASA has described these meteorites as chemical time capsules, preserving hints of the universe's original asymmetry. Life may have inherited this directionality billions of years before Earth existed. Why left-handed amino acids and right-handed DNA? Perhaps it is not coincidence. These orientations complement each other. Left-handed amino acids fold into proteins that interact perfectly with right-handed nucleic acids. Swap the orientation, and the chemistry becomes less stable, less efficient. In this way, the bias in molecular handedness is not arbitrary. It is a reflection of fundamental design dictated by physics itself. Even the origin of this bias traces back to quantum physics. Experiments at CERN and Fermilab confirm that some subatomic particles, like neutrinos, always spin in a left-handed direction. This universal handedness, known as parity violation, shows that even the basic forces of nature are not perfectly symmetrical. In 1956, physicists Chien-Shiung Wu and Tsung-Dao Lee proved this through beta decay experiments, demonstrating that the weak nuclear force favors one spin over another. As Wu observed, nature is not as symmetrical as it appears. If even the universe's fundamental forces have a preferred spin, it is easier to imagine that the molecules of life would inherit the same bias. On Earth, this pattern persists. Large-scale systems follow spin. Hurricanes spiral one way in the northern hemisphere and the opposite in the southern. The Coriolis effect, arising from Earth's rotation, dictates this motion. Even our planet's magnetic field maintains a consistent polarity, flipping only occasionally over millions of years, but never losing its fundamental orientation. Zooming out, the universe continues to echo this bias. In 2011, astronomer Leo Shamir studied tens of thousands of galaxies using Sloan Digital Sky Survey data. He found a small but significant preference for galaxies spinning clockwise versus counterclockwise in certain regions. Perhaps this cosmic asymmetry, set in motion billions of years ago, left faint fingerprints that resonate all the way down to molecular structures on Earth. The connection between cosmic motion and biochemistry becomes clearer when we examine light itself. Photons carry spin, which can be right-handed or left-handed. When early starlight passed through rotating magnetic fields in interstellar space, this spin could impart a slight preference on molecules it encountered. Dust grains, floating in galactic clouds, may have scattered light in ways that favored one chirality over the other. Today, the James Webb Space Telescope continues to explore these regions, examining complex organic molecules in star-forming clouds like Taurus and Orion. These molecular nurseries may hold the clues to how cosmic motion shaped the chemistry that eventually led to life. Each rotating cloud, each polarized photon, each subtle twist in a molecule is part of a vast, invisible choreography linking the universe to life on Earth. This is a profound idea. Life may not be merely a product of chance chemistry on a single planet. Its molecular handedness, the spiraling structure of DNA, the folding of proteins, all may be imprinted by the universe itself, a legacy of its earliest rotations and imbalances. On Earth, spin governs larger structures as well. Plants coil toward light in spiral patterns. Seashells and coral grow in logarithmic spirals, and tornadoes and cyclones follow the Earth's rotational bias. Even the behavior of rivers, sand dunes, and ocean currents reflects the underlying spin of the planet. From subatomic particles to planetary motion, from the arms of hurricanes to the arms of galaxies, spin is everywhere. It is the rhythm that unites the quantum and the cosmic, the molecular and the planetary. Tracing this thread even further, the connection deepens. Every star cluster, every galaxy, every polarized photon carries information about the universe's earliest laws, encoded in the twist of energy and motion. Life, in all its complexity, may simply be an extension of the universe's original spin, a living echo of the first rotations set in motion billions of years ago. Take a breath. The DNA in your cells twists to the right. The amino acids that fold into proteins twist to the left. This choice, made before Earth existed, resonates with the motion of galaxies, the polarization of starlight, and the spin of subatomic particles. You are, quite literally, a child of the universe's rotation. And as we trace this connection, a new question emerges. If cosmic spin shapes molecules, could it influence consciousness, evolution, or behavior? Could these ancient currents, responsible for galaxy rotation and molecular chirality, subtly guide life itself? These are questions that modern astrobiology and cosmochemistry are beginning to explore, where physics meets biology and the universe whispers its secrets in the twists of molecules. The universe does not merely host life, it may shape it, spin it into being. From the rotation of galaxies to the polarization of starlight, from subatomic particles to DNA, the cosmos leaves its fingerprints on the molecules that define us. Every photon, every spiral, every molecule carries a message from the universe's earliest moments, a story of motion, imbalance, and the subtle bias that made life possible. Take another breath. Look inward at your own cells and outward at the stars above. You are part of a rhythm that began billions of years ago. The handedness of molecules, the spiraling DNA, the rotation of your planet, and the spin of distant galaxies are connected by one invisible thread: spin, asymmetry, and the directionality of creation. Life, in this view, is not a random occurrence. It is a natural expression of the universe's earliest motions, a reflection of a cosmic preference that stretches from the quantum to the galactic scale. Each living molecule, each spiral of DNA, each fold of protein is an echo of the universe's first spins. And so, as we follow this thread, we see that life itself may be a cosmic phenomenon, written into matter by the universe's earliest rotations. The spin of galaxies, the polarization of starlight, and the chirality of molecules are all part of one continuous story, a universe that spins, imperfectly, yet with exquisite precision, from the largest scales to the smallest. Everything that spins eventually slows down. Days on Earth are getting longer. Galaxies are drifting apart, their graceful spirals losing momentum. Even the stars themselves, those furnaces of energy and fusion, are burning out one by one. The universe, which began with a grand spin, seems to be unwinding slowly. But can motion truly vanish? Or does it just spread thinner and thinner across the fabric of space? NASA physicist Michelle Thaler once said, "Energy doesn't disappear, it disperses. Spin is no different. It doesn't stop, it diffuses." Here on our planet, the process is already underway. Each century, the moon's gravity slows Earth's rotation by about 1.7 milliseconds, transferring energy outward. As a result, the moon drifts away at nearly 3.8 centimeters per year. It's a gentle, billions of years long dance. Laser reflectors left by Apollo astronauts measure this drift with millimeter precision. If it continues, one day Earth's rotation will lock with the moon's orbit, so that each always shows the same face to the other. The tides we know will end. The daily cycle of oceans and winds will fade. Planetary spin, once vigorous, will settle into equilibrium. Elsewhere in the solar system, the story is similar. Mercury is already in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the Sunday. Venus, with its dense atmosphere, now rotates so slowly that one spin takes 243 Earth days, and it spins backward, opposite to its orbit. Even Mars, with a day only slightly longer than ours, is gradually slowing. On cosmic timescales, spin is not eternal. It is a rhythm winding down. Galaxies experience the same gradual fade. Using the Hubble Space Telescope and the Very Large Telescope, astronomers have measured the rotation of spiral galaxies billions of light-years away. Compared with modern galaxies, these ancient systems spun faster, with tighter arms and denser cores. Over time, gravitational interactions and cosmic expansion gradually sap that motion. Collisions and mergers redistribute angular momentum, leaving galaxies rounder, slower, and more diffuse. Spiral arms give way to ellipses. Even the Milky Way is not immune. ESA's Gaia mission has mapped over 1.8 billion stars, revealing that our galaxy is evolving towards stillness. Its outer arms, once tightly wound, are stretching. Billions of years from now, the Milky Way and Andromeda will collide, not in violent chaos, but in slow, silent fusion. Their combined rotation will settle into a massive, nearly motionless elliptical galaxy. Yet, spin never truly disappears, it transforms. When a massive star dies, it collapses inward, conserving angular momentum and spinning faster than ever. This creates neutron stars, city-sized objects that can rotate hundreds of times per second. NASA's NICER instrument on the International Space Station has observed pulsars spinning 716 times per second, their beams sweeping through space with the precision of atomic clocks. Even these cosmic lighthouses eventually slow, radiating energy as gravitational waves and magnetic fields. And then there are black holes, the universe's last great engines of spin. Even they aren't eternal. Stephen Hawking predicted in 1974 that black holes slowly evaporate through Hawking radiation, losing energy and angular momentum over unimaginable timescales. A spinning Kerr black hole gradually transfers its rotation to surrounding space, sending faint ripples of energy across the cosmos. Future missions, like LISA in the 2030 seconds, will detect these gravitational whispers, records of rotation being released into space-time, echoing across billions of light-years. So, will the universe ever truly stop spinning? Not completely. Angular momentum cannot be destroyed, only spread thinner, shared among an ever-expanding sea of particles. In that sense, the universe never stops moving. Motion just redistributes itself. Still, there may come an age when movement becomes imperceptible. Long after the last stars have died and galaxies have faded, the universe may enter the heat death. Energy will be evenly spread. No temperature gradients, no flow, no reason for anything to move. Rotation will mathematically persist, but without contrast or structure, it will lose all meaning. Some cosmologists call this the cosmic silence, the final calm after every vibration, every orbit, every spin. Protons themselves may decay. Black holes may fade into bursts of radiation. Only faint photons and neutrinos will drift endlessly through space, carrying the last traces of the universe's once grand rotation. Even now, when we peer into the past with the James Webb Space Telescope, we are reminded of the universe's future. Each ancient galaxy we see is another tick backward on the cosmic clock, showing us how rotation once defined structure. Its images reveal beginnings and endings alike, motion kindled by imbalance and fading into stillness. Yet the fingerprints of spin remain. The polarization of the cosmic microwave background, the curvature of space-time around dying stars, they all encode the memory of motion. It is not the movement that disappears, only our ability to notice it. Take a slow breath. Earth's core is still turning. Stars still orbit. The Milky Way drifts through darkness. Every motion you observe is a flicker of that ancient rotation, one that will outlast individual lifetimes, though not eternity itself. And when that eternity arrives, when the last spin stretches into silence, something will still remain, not movement, but the memory of movement. Even if the universe forgets how to turn, its geometry will remember it once did. And in this vast, slowing cosmos, another question quietly emerges. If every atom, every planet, every galaxy is gradually losing motion, what does that make us? We are the ones still moving within it, carrying the ancient spin in our own lives. Every atom in your body is spinning. Electrons orbit your nuclei. Protons and neutrons whirl within. Quarks dance deep inside. This motion is not random. It is continuous. The faint echo of the universe's first rotation vibrates through everything that lives. When you breathe, when your heart beats, when you move, you are not separate from the cosmos. You are part of its oldest memory, motion itself. Angular momentum is the persistence of spin, the rule that keeps motion alive. It's why galaxies still turn, why planets still orbit, why atoms vibrate after 8 billion years. Motion carries history. Every rotation, from the tiniest particle to the grandest galaxy, is a story written in the language of spin. According to scientists at NASA's Goddard Space Flight Center, angular momentum is not something that can simply disappear. It cannot be destroyed. It can only be passed along, divided, or shared. That idea alone carries a powerful implication. Every rotation in the universe, from the slow turn of galaxies to the invisible spin of particles, may be part of the same continuous motion that began at the birth of everything. At the very beginning, the universe was not silent or motionless. Data from ESA's Planck satellite reveals that the cosmic microwave background, the faint afterglow left behind by the Big Bang, contains tiny irregularities. These are not random. They are slight differences in temperature and direction, subtle anisotropies etched into the oldest light we can observe. Some cosmologists believe these patterns are remnants of the universe's earliest angular momentum, the first imbalance that set matter and energy into motion. That initial twist never vanished. Instead, it broke apart and spread outward, cascading down through scales, from vast galaxy clusters to individual atoms. When stars are born, enormous clouds of hydrogen and helium begin to collapse under their own gravity. As they contract, they start to rotate faster, following the same principle that causes an ice skater to spin more rapidly when pulling her arms inward. This conservation of angular momentum shapes everything that follows. It forms spinning accretion disks around newborn stars, gives rise to planetary systems, and feeds the rotating maelstroms surrounding black holes. Every planet, every moon, carries a fraction of that ancient motion within its orbit. And inside those worlds, within their rocks, their oceans, and eventually their living cells, the pattern continues on smaller and smaller scales. Even the atoms that make up your body hold a record of this motion. Electrons, the particles that determine how atoms bond and how chemistry works, possess an intrinsic property known as spin. This is not a literal spinning like a tiny planet, but a fundamental quantum characteristic that defines how particles behave and interact with magnetic fields. Without it, chemistry as we know it could not exist. NASA's quantum research initiatives describe spin as one of the foundations of atomic order, the difference between stable matter and chaos. In that sense, all matter follows an ancient choreography. Particle spin gives rise to magnetic fields. Magnetic fields enable structure. Structure allows stars and planets to form, and within those planets, life eventually emerges. The electrical signals that fire across your neurons are shaped by these same principles. Every thought, every memory, every sensation is the result of charged particles moving in coordinated patterns. So when we ask whether consciousness might be the universe remembering its own motion, the question is not merely poetic. It is grounded in physics. Each brainwave is built upon rotational behaviors that trace back to the earliest moments of time. The magnetic fields produced by your neurons are incredibly weak, yet they follow the same electromagnetic rules that govern pulsars and magnetars, some of the most extreme objects in the cosmos. As astrophysicist Neil deGrasse Tyson once put it, we are not simply in the universe, we are part of it, and it is part of us. From a scientific perspective, memory itself is the preservation of patterns. Information is stored in physical states. Atoms retain orientation through spin. Cells retain memory through molecular arrangements. Stars retain history through their rotation. And the universe retains memory through the geometry of space-time. Einstein's theory of general relativity shows that energy and momentum shape space-time itself. Every movement, every rotation, slightly curves the fabric of reality. This effect, known as frame dragging, was confirmed in 2011 by NASA's Gravity Probe B mission. The experiment demonstrated that Earth's rotation gently twists the space-time around it, like a spoon slowly stirring honey. Spin, it turns out, is not confined to objects alone. It reaches outward, extending into space itself. In the same way, even your own movements, though unimaginably small on cosmic scales, also disturb space-time, however faintly. The difference is one of magnitude, not principle. The atoms in your body spin billions of times each second, generating magnetic interactions that can now be detected by ultra-sensitive quantum instruments. Each microscopic rotation contributes to the ongoing record of motion that began long before life existed. If all motion leaves an imprint on space-time, then perhaps awareness is simply the universe encountering those imprints through complex systems like us, not as emotion or spirituality, but as continuity. Consciousness, in this scientific sense, is a system reflecting its own internal state, and that reflection is written in movement. Even light, the universe's great messenger, carries angular momentum. Photons possess spin, which determines how light becomes polarized and how it interacts with matter. The polarization patterns found in the cosmic microwave background are the oldest surviving record of rotational history. ESA's Planck mission and NASA's WMAP mission mapped these patterns in remarkable detail. revealing faint, swirling structures known as B-modes. These are thought to be signatures of primordial gravitational waves, ripples, produced by the universe's earliest motions. When you look at starlight, you are literally seeing the memory of spin light twisted, stretched, and shaped by billions of years of motion. That light enters your eyes, triggers chemical reactions, and becomes part of your own neural activity. In this way, the universe doesn't merely remember its motion, it continues to experience it through every observer it creates. As the cosmos expands and cools, these traces do not disappear. Galaxies may slow, but their angular momentum is never lost. It is transferred into surrounding gas, into dark matter halos, into radiation. The James Webb Space Telescope has already observed faint filaments of gas connecting ancient galaxies, structures shaped by these exchanges of motion. Every strand of matter still moves in rhythm with a pattern established 13.8 billion years ago. And when the last stars finally fade, when motion becomes nearly imperceptible, those patterns will remain, encoded in gravitational waves, frozen into particle spin, stretched thin across ancient photons. They will persist as the universe's deepest record. Motion preserved, not as activity, but as form. Like fossils of rotation, they will define the shape of whatever remains. Carl Sagan once reflected that we are a way for the universe to know itself. In the language of physics, that knowing is not mystical. It happens through motion, energy, and spin. The universe continuously records and retrieves its own history. Take a slow breath. Every atom within you still carries the same rotational heritage that once ignited the first stars. You are a moving archive, a living extension of the universe's memory. And if motion is memory, then perhaps life is the brief moment when the cosmos pauses just long enough to notice that it is still turning. If this quiet journey has given you even a small sense of calm, I'm grateful you spent this time with me. A gentle like or a soft tap on subscribe helps keep these cosmic reflections alive. And if you feel inclined, tell me where you are listening from and what time it is there. I love seeing how these quiet stories drift across the world, from one sleepless corner of the planet to another. Your presence matters. Even your silence does. Until next time, may the universe turn gently around you.